Welcome back, college algebra people. We are on section 2, talking about linear functions, and now we finally actually are talking about linear functions. So subsection 3 is about constructing linear functions, and that is precisely what our learning objective is: construct the equation of a line, either given 2 points or given a point and a slope. So we've been teasing for the last couple of videos about what this section is really about, these functions that have this kind of interesting characteristic, and here's where we actually see it. So there's our definition. So a linear function is a function with the characteristic that for any points in its domain, the average rate of change between those points has the exact same value. So we saw this for one example a couple of videos ago. We calculated average rate of change for a function that has this form. It looks like some constant times the variable plus some other constant. And we did it in one of those weird cases where we didn't have numbers for the interval. We had some letters like a and a plus 1, something like that. And we found that in spite of the fact that we had no numbers for that, we came out with a concrete value for average rate of change. In other words, it didn't matter which 2 points we picked, that value was going to be the same no matter what. And so that's what we're calling slope in this case. That's kind of the thing that gives a linear function its claim to fame. It has that exact same constant a, no matter what values we may pick for the interval. B is this other constant, which has a cool kind of visual geometric interpretation too, but we'll sort of see that fall out when we practice this. So we can compute slope, so this average rate of change thing, by this computation. I guess if you're really thinking carefully about this, this is just average rate of change. This is, instead of calling it f of t2, we're calling it y2. We're just giving it this output name. And then instead of calling it f of t sub 1, we're calling it the y1. So this is basically the a and the b on the bottom, and when we were looking at the average rate of change definition, and this was f of b and f of a on top. It's just a less fancy version of it, basically. So this is saying, because the slope is the same no matter what points you pick a couple, or take the 2 that you've been given, for instance, in the problem, and then you can calculate slope there, and you'll know for this type of function that will always be the same. That's what this characteristic is really doing for us. So as a quick example of this, so let's find the slope of a line between these 2 points. So our slope a looks like, there's no particular reason to use a. It's the first letter of the alphabet, so we might as well go with a constant. And actually, if you'll permit me a brief aside, because you're probably looking at this going, Mike, I've seen linear equations before, and this does not look like a linear equation. So you might know a very similar form of this that just uses different letters. Y equals mx plus b. And there's no reason to use these letters either. X's and Y's, I've gone off on my little mini tangent about that before. There's no good reason that anyone can come up with for why we have to use X's and Y's for our variables. And M is even mysterious. If you're thinking about slope, and this is the constant that represents the slope of a linear function, then maybe S would be a good letter, S for slope. The best that, to my knowledge, and feel free to put in the comments if you like, if you know, but to my knowledge, the best guess that we have for this is that the French word for to climb is, and pardon my butchering of a beautiful language, monter. And so if you think of climbing as like a slope, then M would be a pretty decent letter to start that out. And gasp! Not only English speakers are the ones who came up with mathematics. In fact, the history of mathematics is filled with almost entirely non-English speakers having developed most of the good stuff. So in any event, having a French word for this might not be crazy, but we're using A and B as just kind of the laziest first letter and last letter of the, first and second letters of the alphabet to represent these constants. Okay, so there's my aside about slope, my little mini tangent. So for this calculation, we are given this formula right up above, very helpful. So we get to use kind of whatever points we might want. Y1, let's actually write the correct things here. So I need like things together, y's on top and t's on bottom. And so we have a couple of points. It's really up to us to pick which one is which. But for instance, if this was the first point, then we're looking at t sub 1 and y sub 1 that pair together there. And so we'll build our little fraction. And okay, so t sub 1 was just 1, so that's part of our denominator. And then y sub 1, the output would be 6. And our second point, here's our t sub 2 and our y sub 2. So t sub 2 would be first value there, and then over to 14 for our output. Great. So as long as you get the order of these things correct, you're totally fine. So if you got, if you picked 3, 14 to be your t1 and y1, that's great. As long as this is t2 and y2, you'll have flipped everything around, and then you might remember how fractions work. You'd have the negative of what you got on top and the negative of what I got on bottom, and then you'd have negative, negative, and they would get the same result in the end since those signs would cancel. So we'd have 8 on top and 2 on bottom for a total of 4. So if you had done this by making the other choices, you would have negative 8 over negative 2, and then that's the same result though, still having a slope of 4 either way. So calculating slope is all well and good. It's always nice to have kind of the visual perspective on this. So once we have this really nice classic canonical characteristic of a linear function, or any function, but slope for this particular function, then we like to see how that plays out visually, what if impact that has on the graph of a function, because a lot of what we do in this class is just that interplay between different function presentations. What's it look like as a formula? What's it look like in a table? What's it look like in words? And, of course, the graphical perspective. So here are 3 classic expressions for lines based off of this slope. So there's other things that make this special, namely that other constant, b, that we haven't done a whole lot with, but slope being positive puts us into the territory where the function heads upward to the right. And so we have a positive slope in that case. In other words, we have a would be greater than 0 in this first case. A negative slope, as you move to the right, then the graph is falling. And for a 0 slope, then the graph stays totally horizontal. And it's just basically by agreement over the centuries that we move to the right on the graph. We decided, at least sort of, most Western cultures, we have the reading from left to right. So as we move from left to right, that takes us toward larger and larger x values or input values. And so we choose that as the default direction. And I basically just picture myself as a little tiny person walking along this graph. And as I walk to the right, I am being forced to go uphill. And that's where I'm thinking about this positive slope. It's the exact same mentality when we're thinking about increasing, decreasing constant. So that we can relate back to that previous subsection when we're thinking about it. And then what's great visually is that every time you have a positive slope, this line is increasing across its entire domain. So if you have a positive slope, you know right off the bat for a linear function, then this will be always increasing. If I have my silly little stick figure instead walk to the right on this function, then it's headed downhill forever, so there's our decreasing conformation, and then 0 slope is constant here. So we get a function that has kind of each of those characteristics built into it, and it never changes its mind, it never changes direction. So we still haven't done the namesake of this subsection, which is to construct a linear equation. So typically you're given one of 2 different sets of information, and it's basically the same approach regardless of them. This is the situation where we're supposed to find a formula where we're given a slope and a point, which is great. That's plenty of information for us to work with. So let's see if we can dig in here. So finding a formula for the linear function. So one of the things that humans, all of us, struggle with is whenever we're presented with something that's related, very proximal, very, very closely related in time, for instance, to a definition like linear function, then those things are fresh in our head, and it's pretty easy for us to kind of, spit those back out again. What's challenging is in, say, 3 weeks, when you are taking a midterm exam or taking a quiz over multiple sections, for instance, the the glue that sort of ties your brain to a topic kind of loosens a little bit because it's trying to go in a bunch of different directions. You're trying to think about many different topics. So I want to accentuate, even though now it feels sort of silly because there's only one thing we're really finding formulas for, and they are linear functions. But I want to stress that when I read through this and I see formula for the linear function, that's going to help me later on in the course to distinguish between this particular type and all the other types of functions we're going to be running into. Quadratic and exponential and power functions and logarithmic and all this good stuff. So knowing these key phrases now, the fact that we're thinking about a linear function is going to help us sort of narrow down all those options in our brain. So what this gives us is that for a linear function, I know that our formula is going to look something like a times t plus b, and it's our job to figure out what these constant values are. So now we need to find, in fact, I think to be consistent with earlier things, I'm going to write goal. So find a and b. Yes, it's very cute if you say find a and b and then you circle them back in the constant in the formula and say, look, I found them. There's a and there's b. I've seen those little comics too that make their way around the internet. Adorable. What we really mean is find the values for these constants though. Okay, so what other information do we have? I'm working my way through the color palette here. So we also know right off the bat a really important piece of information. We know that the slope is -1/5. And that gives us this constant, like right off the bat. We know that the value of a is going to be -1/5. Perfect. That's fantastic. That's one of our two constants already in the bag. And then we also know that the graph passes through, or contains, depending on how you want to think about it, this point 20, -6. So delightful. Let's see. That means that if we kind of tie together all the things that we know, we ought to be able to take this slope as the value of a, and one of these points, here's a t value, and here's a, I guess technically q value, the output of this function. And if we tie together those two things with this formula, then the only thing that would be unknown is the value of b. And that's great because that's the thing that we're after right now. So now we're going to solve. We'll start with our f of t, and basically what that point has given us is one little snapshot, one particular point in time where we know the input and the output for this function. And so it's not always going to be an output of -6. It's not always going to be an input of 20. I guess it will always be a slope of -1/5. That's what it means to be a constant. And then this b is the only thing we're not sure about. So we're leveraging this one little point in time where we know the input and the output to help us figure out this unknown constant. A little bit of simplification. So there's -4. There's b, and then the last little bit, if we add 4 to both sides, what we're down to is, oh, those little dots bug me. Hopefully they don't bug you as much as they bother me. And now we have a constant of -2. Fantastic. Maybe I'll put a check mark on this guy too. He deserves it. So that's all of the work for this problem. But remember, let's go back to our actual goal. So we found the values of a and b, but the original question said find a formula for this linear function. So before we're all done, we've done all the hard work. Now it's just the victory lap, basically. So in the very end, we're going to write finally, then we'll write the actual formula for this. So f of t is, we got -1/5. I'm going back to t though, because what we want to build is a recipe. We want to have a function that has some output given some input. And so the only things that are in this final expression that have concrete values are the constants, the value of a and b that are never going to change. So here's our actual formula, which is fantastic. Certainly deserves a box. And so there's our linear function, which is great. And it does have the right form. It looks like it is a constant times variable plus some other constant. Here it's plus -2, but still, that counts. And then if we're supposed to sketch a graph of this thing in the TQ plane, one thing to notice from this is that if we, t equals 0 is always a great spot. If that is defined for a function, that's a great place to start thinking about the graph. So if we are going to have our graph in mind and we try t equals 0, what you'll notice is f of 0 is, well, if I plug in 0 for t, we've got negative 1/5, it's 0 and minus 2. And so that 0 times negative 1/5, whenever you plug in a 0 times that slope, it's going to go away no matter what. So one of the lessons that you might take away from this is, since this is always going to go away, give me a line, there we go, then the output when t is equal to 0 is always going to be b. So that's actually a really helpful little tidbit of information here. So this negative 2, what this tells us is that b is the, in this case, the q-intercept. I know you're going to hate that. You're shouting at your devices right now. It's the y-intercept. Fine, you like y, but in this case, we're forced into t. So, sorry. our vertical axis variable, the variable that's being measured on this vertical axis is q, so we're stuck with q instead of y. Again, as I mentioned before, I'm sort of consciously trying to shake you out of these habits, that there's no particular reason we have to get stuck on x's and y's, and we really ought to be able to understand these same concepts without the exact same letters being used every single time. So what we have so far for our graph is, maybe orange is a decent color for this, is that at t equals 0, we still have an output of negative 2. There's b, essentially. And then we could continue to plot points, but I actually want to basically leverage the fact that we have this slope to continue to get us new points. So what that slope tells us is, if we go, and I'm just going to use the negative in the numerator here for convenience. So let's think of this as negative 1/5, same fraction. But that means in order to get a new point, we go down 1 and then over 5 units. So this is not actually part of our graph. This is just us kind of tracking things. But that means a new point on the graph of this line could be found 1 unit down and 5 units over. So I skipped away from our lavender there too quickly. So this is negative 1 and positive 5, basically. Down 1 unit and 5 over. And that's exactly what our slope is. A change in the numerator divided by the change in the denominator. So the change in outputs on top and divided by the change in inputs on bottom. So we've sort of run out of graph. We could try to sort of graph off the page here if we wanted to. But maybe it also makes sense to go in the other direction. If you considered this fraction instead with the negative on bottom, then it's positive 1 over negative 5. That's the same fraction too. That just means you can also get new points by going up 1 and back 5 units. So that's plus 1 and down 5. I still have to make sure I'm using the numerator as outputs and the denominator as inputs. So the top is like our Q thing and the bottom is like our T thing. But that gives us new points on this as well. And then because I will likely embarrass myself drawing this line, I'll use the actual line feature. See if I can't connect the dots. Okay. So in theory, this would be continuing forever. Lines without, at least without other constraints that we put on them, have domain all real numbers. And so there would be our picture. And hopefully that would be confirmed if we were to plot points and do kind of that classic graphing approach as well. One other little check that we can do on our work is whether we would be vaguely convinced that 20, -6 would actually fall onto this picture. And our graph doesn't extend that far because we were much more conservative with our values. We did, 1, 2, 3, 4, etc. So our axes did not extend out to actually include 20 for our inputs, but you could sort of picture that by the time we get out 20 units over here, sort of off your screen a ways, that it would have dropped down to a height of -6. It's really not falling all that rapidly, right? It only goes down 1 unit for every 5 units over. So 20, -6 could plausibly be on this graph. You could also check that if t were equal to 20, that the output of this function would be -6, and I believe it would be. One other quick note if you, another thing, you may have been shouting at your screen here. I'm sure there's lots of things. But you might have used the slope-intercept, or heard of the slope-intercept before. Sorry, the point-slope form before. So have you used the point-slope formula? I feel like this is one of those infomercials where it's like, have you ever had this problem? Have you ever run into a situation where you've got a point and a slope? Do you need us to fix it? Too bad. It's your job to fix that problem now. I'm handing it off to you. So if you use point-slope formula, oh, that's a question. I suppose that should end in a question mark. So that's fine. So the point-slope formula looks like instead of I'll use it without the function notation, but if we use the same kind of input and output variables and constants and stuff, so if A is the slope and then T1, Q1 is a point. So it's exactly what it sounds like. Point slope formula is built for the situation like this one where we've been given a slope and a point, and it's another way to get an equation for a line. So I'm fine with using this. Use it. Why not? I'm reluctant to pile, I know there's so much in this class, so I'm reluctant to give you another formula for something that I don't feel is absolutely critical. If it doesn't really give us something that another tool doesn't, then I'm reluctant to kind of add that to the all the complicated stuff that's floating around in your brains. So because this form of a linear function is so usable and it gets us to the solution just fine, and it also matches the basic definition of what a linear function is, I'm reluctant to give you a new thing to say, yes, you must also know this other thing. So if you have used the point-slope formula and you like it and you want to keep using that, that's fantastic. If you've never heard of it, you can just sort of erase this from your brain if you don't feel like stuffing yet more stuff in there. So I figured I would at least, I don't know, it's splitting the difference somehow. I'm not requiring it. I didn't want to completely ignore it because you may have seen it before. So I figured I would at least mention and say, if you have, it's a totally valid tool for the class, but it won't be something that I'm requiring of you. Okay. So the rest of this section is kind of more of this, but we're going to try to layer on some of that good word problem action. So we'll be back with modeling based on descriptions.